Good morning. So today I'm going to talk about who we are, what we do, and data science, specifically machine learning and artificial intelligence. Western Digital is a global leader in storage technology. So traditionally, we are very good. We are leaders in the hard disk space, and we are also leaders in the flash memory space. And you might know of flash. Flash is the greatest invention, in my opinion, because it has allowed us to have very fast data access and given birth to all of this proliferation of devices. But now, we're in the process of creating this new, what we call storage class memory. I'm going to show you a picture of a two-dimensional NAND architecture. Pay attention to the floating gate, pay attention to the word line, pay attention to the bit line. Now, on a two-dimensional NAND structure, we are physically running out of ability to place more cells. And the reason is because we have a physical structure. And in that physical structure, we can put 4 cells, 16 cells, 32 cells, 64 cells. After that, we can't go anywhere. So we have to create a three-dimensional structure. Think of this as a multi-story building. And when you think of a multi-story building, you're thinking of very stacked complexity. We're going to come back to this in a minute. So for us, all our wafers are manufactured in Yokkaichi, Japan. And in Yokkaichi, Japan, we have our manufacturing fabrication units, and there we create our wafers. Could you imagine how tall this wafer stack could be? So here's some comparison data, right? You have Mount Fuji, 12,388 feet, and we are creating wafers the size of Mount Kilimanjaro. Now, I want to show you what a physical wafer looks like. When I found this, I was so excited. This is silicon. And inside the silicon is a little die, tiny, tiny little die. And this little tiny piece of die actually goes into USBs and SSDs and your device. I don't have the smallest die that I could show you, but it's a very tiny little die right there. And so that's what you're seeing when you look at the picture. So now we are in the process of creating this three-dimensional NAND. And here we are. So we have to figure out how to scale three-dimensional NAND. And we're looking at a 24-layer. Then we look at a 48-layer. We're pretty much talking about a 64-layer, and then dominance in the industry. So this invention of three-dimensional NAND is what we are about. And this three-dimensional NAND is going to get us to the skyscraper of memory technology. Very excited about that. Now we're going to talk about our first use case and how it applies to machine learning and artificial intelligence in this domain. So we talked about three-dimensional NAND. I'm actually going to talk about a little bit about how it's created. So when we create the device, we actually have alternate layers of oxide and nitride. And one of the layers is a conducting layer, and the other layer is a dielectric layer. And what we do is we actually create a vertical trench between the two layers to connect the different memory layers. And when we create this vertical trench, it's what we call a memory hole. Very important to know. And then we fill the memory hole with actual materials. So creating millions and millions of wafers in a year, I get a ton of memory holes. Okay, so that nice picture on the side is what we'd like to get, but that's what I actually get, right? So the picture is not great, but we get millions of these images. And we have to go through these images and start denoising these images. They come with very, very high noise at the scale of millions. And after we start denoising, we have to look at the pattern. The pattern at the top is very different from the pattern at the bottom of the image. And also, why it's important? Because we have to look at the dimensionality and the variation between the top and the bottom. Then on top of that, we have sub-patterns. So if we go back and just look at this image over here, you can see that it's not quite a donut. They all look a little bit like donuts, but they're not. It's actual deformation in the memory hole. And sometimes in each of the memory hole, there are sub-patterns. So within the circle, you might have a sub-pattern like an ellipse or a triangle or even a heart, which we don't want. What we want is perfect memory holes. And so we go through the process of curation, and then we actually do classification. And we use machine learning techniques. We start doing complexity in the training because there's many, many nested sub-patterns which we have to detect. And then we use random forest and decision trees. We've used many different methods to do the classification and the clustering of these patterns. We look at very advanced techniques like elastic bunch mapping, graphing. This was used by the FBI for facial recognition. And we calculate through complex mathematical algorithms. We have to figure out the exact roundness of the memory hole as we start to invent and create new three-dimensional memory. We're also looking at what would the radius look like, what would the perimeter look like, how do we look at the curvature, and we also have to then balance all of these different things on top of our classification and clustering algorithms to then detect the sub-patterns and arrive at non-warped memory holes or less deformed memory holes so we can get to mass production in our factories from simply creating a new technology node. So let me go to the second use case. And here I'm going to talk a little bit about correlation and ranking in the machine learning class of problems. So most companies, most industries, I actually come from search background and I come from advertising industry. In that industry, we created a lot of products and then we went out and created data and we tried to understand our products and then we did better. So the reason for the data was really to make us better in our products. And to get better at clicks, we used to look at the bag of words and try to do machine learning, try to figure out how we be more relevant to the advertisers that came to our site or to the users that was using our site. But in this domain, it's a little different. In this domain, what we are doing is we actually create data. Can you imagine that? We actually create data. And then we invent products, completely new technology nodes, to then go out and bring revenue to the company. So here is a screen that shows you the process. So we have this extensive manufacturing process. I've really dumbed down this image so you can understand the complexity involved with it. There's a lot of manufacturing data, and we do a bunch of things: lithography, etching, prepping, clean room, tool configuration, so on and so forth. And then we go through very series of measurements to make sure that we've got our memory holes correctly. We've got all of the elements of the wafer that is quite good for a market viable product. And then we test the heck out of it to make sure that we meet all the criteria. Not only the criteria that the wafer is very high yielding, but also the criteria that the wafer has long endurance. When we test the wafer, we want long lifetime for the wafer. And these two are somewhat conflicting goals. So as we look at the wafer and as we, cost per bit is sliding down. So there's lots of pressure to create the smallest, tiniest bit with the lowest cost possible. And so we are very cost conscious in that we can't lose a single bit of silicon. If we created silicon and we can't use the silicon, it's loss of device, and we don't want to do that. Right? And so then we create our screens to test for the different endurance cycles. And sometimes we are able to do very good machine learning to try to predict how will the device perform. If the device has performed at 10,000 cycles, how will the device perform at 5,000 cycles? Or how will the device perform at 20,000 cycles? Because we can't test for every single cycle. And so we look at different correlations. We look at correlations that are single factor, and we also look at correlations that are multi-factor. But I want to leave you with this couple of last slides. We have a lot of challenges in the manufacturing industry as we apply new technology to node creation: material instability, deformation, material buildup, substrate overheating, heat sink, resistive loss, deposition issues, thickness, warpage and bending, wetting oxidation layers issues, and then diffusion barrier and DPPM. DPPM is defects per parts per million, and we have a certain threshold for defects per parts per million. If we overcome that threshold, we don't have a market viable product. So we have to care about all these. And how do we care about this? Because we built a corpus of knowledge, a corpus of intelligence. This corpus of intelligence allows us to understand structural anomalies, non-structural anomalies, instant-based anomalies, and correlations that actually matter to us. So dealing with heteroscedastic data, machine learning involving model building and repeated learning, ranking and weighting, and also using some of the very good machine learning algorithms that's out there. But for us, this is a very iterative process. And my last slide and key takeaway for you guys is really, the world has not seen heteroscedastic data. And the reason the world has not yet seen heteroscedastic data is because we have not truly come in the age of internet, industrial internet. Hundreds and thousands of test equipments generating data at massive scale coming to us near real time. When we look at heteroscedastic data, that is the leading edge of data. And that leading edge of data is highly complex in nature. You're going to see correlations that look like this with different failure maps. And we have to figure out, how do we find the pattern in that? What is a structural pattern? Where are the strong signals? And how do we deal with those signals? If I measure the computational complexity of this data, it's at quadratic levels right now. But I expect it to be at higher levels of complexity. And we need to be able to tame this data. That's why we're trying to build this corpus of intelligence, which will actually help us. But I think that we will soon be getting into this highly variable, near real-time data coming at us from the industrial world. And we have to learn how to deal with that. Thank you very much.
Oh, thank you very much, Janet. You get the prize for the fastest speaker. It's great. That means that we just have a little bit more time for questions, which is wonderful. So fire away.
We talked about heteroscedasticity. I mean, this is something we deal with every day in Wall Street. You know, it's kind of day in and day out. So have you looked at different models that we use, like in the bond markets, derivatives, yield curves? I mean, heteroscedasticity is pretty much our bread and butter. So have you looked at that? And
for you, I think there's a little bit of help. That you have trend data. You see, so trend data is kind of indicative, a little bit indicative. We have no trend data. It's like when we start out with a new technology node, we're starting out with a recipe we don't know if anybody will like. It's like cooking, right? You throw in one thing, you throw in another material, you throw in hundreds and thousands of processes. You're trying to converge very quickly to a technology node that somebody will accept, the market will accept. Right? That's the variability. But I agree. I think the stock market is a classic example of heteroscedastic data.
Hi, next question.
Hi. Suddenly my brain went blank, sorry for that. I was wondering what sort of skills you're looking for somebody, sorry, I'll stand up so you can see who I am.
Yeah, this is...
What sort of skills are you looking for somebody who can do this kind of work? Because it seems like you need somebody with some specialized hardware knowledge and some specialized data knowledge. And I guess also I was wondering, I mean, these sorts of chips have been tested for a really long time, and you know they do electrical and functional testing, and what's better about visual testing instead of those?
Absolutely, very good question. So the skill set, I would say that first, ability to ask critical questions, never giving up, and having a passion to go deep as you can, no matter what domain you're in, that's enough. I think you really need to stick with it. Even when your data is not giving you all the answers, you got to dig, because the domain people know. I'm not from this domain, by the way. And I've learned so much about this domain because I have interest and I want to know, and I want to know whether the answers the data is providing me is viable or not. I want to be able to go to my stakeholders and say, I'm not just academic in my results with the machine learning. You can implement the memory hole algorithms in production and watch 90% accuracy on the return of that investment. I want to be able to say that to my stakeholders, and I'm proud to say we were able to accomplish that. Your second question around, your second question was around, could you repeat the question, please? Oh, yes, I got it. So your second question was around domain experts. You're absolutely right. Domain experts have been testing and they know, but imagine domain experts were looking at 10,000 memory holes and then they were looking at 20,000 memory holes just by their domain knowledge, right? And then suddenly they have 1 million memory holes to look at. And I remember one of the domain experts came to us and said, Janet, we need desperate help from your team because it's taking us 8 hours. And these are not ordinary people. These are device physicists. These are material scientists. They know with one look whether, because of years of experience, they understand the domain so well. But this is an area where data science can help them. Data science is not trying to, it's augmenting their capacity to work better, right? So the data scientists and also the machine learning models are helping them. So the feedback I got was, Janet, let's go take other patterns that's coming out of different other tools, and let's look at those, right? So it is very interesting because the domain is so closely held by people who know the domain to suddenly say, let machine learning do most of the work. But I think that machine learning can augment very well and make the people so much more smarter.
Time for one more quick question. Oh, there's a Twitter question. Let's do that one.
So we have a question from Twitter. It says, IT is not always friendly to women. What can women who are already in data science do to help recruit more women into the field?
Yeah, my thing is we're just here and we're not going away. So excellent. We're here, the women are here. So we're not going. And so we just have to get the word out, advocate for ourselves, and just do a great job.
But men, don't be intimidated, right? We're nice. Thank you so much, Janet, for that wonderful answer and for your talk. That's wonderful.